Hi everyone, this is Mrs. Jackson. This is Chapter 4, Section 1, Part 1. In this very first video, we're going to ask ourselves, what is a rational expression? In this section, we're going to learn how to recognize a rational expression, as well as how to simplify it. And the final thing we're going to learn is how to state the domain, the valid domain for this expression. So to talk about a rational expression, I first want to reference that or compare that to what a rational number is. So as you know, a rational number is can be written as the ratio of integers. In other words, a fraction. So if we take a look at some examples here of rational numbers, I'll write a few here. A whole number, maybe the number 10. The number 10 can be written as a ratio of integers, 10 over 1, for example. A mixed fraction, 4.5. A mixed fraction, like 4.5, can be written as 9 halves. So that is a ratio of integers. Let's look at a decimal. 6/10. 6/10, a decimal is actually a fraction, base 10 fraction. We could write this as 6/10. And finally, even a non-terminating decimal, such as 0.33 repeating, that is also a rational number because it can be written as 1/3. Now, what are numbers that are not rational numbers? Well, certainly we know irrational numbers are not rational. So just brush up on what irrational numbers are. Of course, pi is a non-terminating decimal that does not have a repeating pattern. Any square root of an imperfect square, such as square root of 2 or square root of 5, anything like that would never be able to be written as a ratio of integers. And later on in the year, we're also going to be talking about the natural base e. It's a fixed number, much like pi, but it also does not terminate and it does not have a repeating pattern. So all of these here, irrational numbers, are not rational. So what are rational expressions then? Well, as I said, think fractions. Only this time, with a rational expression, we have algebraic expressions, and they can be written as the ratio of two polynomials. So, example, I could write maybe 2x plus 1 over x squared minus 5, or 1 over x squared minus 2x plus 1. So both of these would be examples of rational expressions. So how does one go about simplifying a rational expression? We simplify these expressions in the same way that we would simplify a rational number. So in simplified form, we are going to reduce all of the common factors that are in both the numerator and the denominator. So let's first take a look at how we simplify a rational number. To illustrate this, I'm going to break down both the numerator and the denominator. So I'm going to start with my 144, and I'm going to do some prime factorization. So when I see a number 144, I think 12 times 12. And of course, 12 is 3 times 4, which is 2 times 2 times 3. So I've got 2 times 2, that gives me my 4, times 3, and I have the same thing over here. 2 times 2 times 3. So I can rewrite the number 144 with all of its factors. So I'm going to do that down here. I've got 4 2's, and I've got 2 3's. Now I'm going to break down 180. I think I'll change colors here. So 180, I think 10 times 18. And 10 is 2 times 5. And 18 is 3 times 6. So I'm going to write this as the 6. I'm going to write as 2 times 3. And then I have another 3 here. So I can write the number 180 as 2 times 2, 2 times 2 times 3 times 3, and then I have a 5. So I've rewritten equivalent numerical expressions for both the numerator and denominator, and I can't have any common factors left over. If I have any in the numerator and the denominator alike, I'm going to reduce those to 1, because anything divided by itself is 1. So these 2's reduce, these 2, and these 3's, and these 3's. And so my final reduced rational number, I have 2 2's up on the top, which is 4, and on the bottom I have 5. So 144 over 180 reduces down to 4/5. Now how does this apply to rational expressions? So I have a rational expression here with x squared minus 4 on top, and I have a quadratic polynomial on the bottom. And I'm going to need to factor these in order to see if I can reduce this in any way. So we can see that the numerator is a difference of squares. I'm going to abbreviate. And the denominator is a quadratic that we're going to factor. So I'm going to say quad factor. Okay, so in the top, we see x squared minus 4 can be factored to x plus 2 times x minus 2. And the denominator has a quadratic, and I'm going to take some shortcuts here. It has a quadratic whose a equals 1. And when that happens, I don't have to go through all of the work to do factor by grouping. I can just look for two numbers that multiply together to give you your negative 10, because a is 1, and sum to give you positive 3. And so the numbers that I'm looking for would be 5 and a 2. One has to be positive, one has to be negative. And in this case, our 5 is going to be positive because we are looking for a positive 3x. So you can see here, if I multiplied these back together, 5x minus 2x is going to result in that positive 3x. So now we're factored, both in the numerator and the denominator, and we're looking for any common factor that can reduce. And we have an x minus 2 on the top and an x minus 2 on the bottom. Anything divided by itself reduces to 1. And so in the end, this rational expression can be reduced or simplified to x plus 2 over x plus 5. Now, just like rational numbers, we need to worry about what that denominator looks like in a rational expression. For example, in a rational number, we could never have this 4/5 over here. We could never have 4 over 0. We never can have a 0 in the denominator of a fraction. And the reason for that is it results in an undefined expression. Why is that? If I have 4, I'm just going to put a little example here. 4 divided by 2 equals 2 if and only if 2 times 2 gives you back the 4. So if I have 4 divided by 0, what times x here is going to give you back the 4? There is no such number. Anything multiplied by 0 is 0. And that's why we can never have a 0 in the denominator. It's undefined. I'm going to write that down here, undefined. And so when it comes to rational expressions, we have to take one additional step and basically write the domain that this expression is valid for. So here we have a reduced expression, x plus 2 over x plus 5. I can't have this expression be valid for all real numbers because there are numbers that are going to result in 0 in the denominator. And hopefully you can spot one right away. So I'm going to write here that the domain x cannot equal -5. I think you can see that if we have a -5 here, then my denominator will result in 0. So far, so good. However, we have to go back to the original factored denominator here. And when we do that, you can see that I have to also exclude x equals +2 because that will give us a 0 in the denominator. And if that confuses you, because it did cancel, if you will, it reduced out to 1. If I put x equals 2 back into this original quadratic here, I've got 2 squared is 4 plus 3 times 2 is 6. So that's 10 minus 10. That x equals 2 is also going to give me a 0 right up at the top. So the idea here is that you have to look at all the factors in that denominator and exclude any values of x that will create a 0. So the takeaway here, the big caution at the bottom is when you look for your exclusions, so when you're looking for any domain to be excluded, you have to look before you look at these simplified forms. So you have to go all the way back to the original factoring. Okay, so now in this video we learned what a rational expression is and how to simplify it, and finally what domain has to be excluded for that expression to be valid. Thanks for listening. Hope this helps.